Good morning, good morning, good morning, good morning, and welcome. I don't know how early you got up, but it was. If I can stop that, because if I have to do these two things at the same time, I will collapse and go down into the basement, and then there won't be any lecture, and there'll be tears everywhere. I don't know if you got up early this morning. It was foggy, kind of not too cool. And that's burning off. It is gorgeous out there, so I hope you've got some plans to enjoy the outdoors later on today. Well done. Let me kind of move this around here. I like this. I like the drawings. I like my compatriot there that looks somewhat like he's giggling in a sinister, like, and he's kind of pulling my strings, and I am the puppet of the plankton. I am the puppet of the plankton. Good morning and welcome to Zoology 3700. Give me a second to clear those. Thank you for that. Don't lose your annotation tool because we're going to use it again. And the other thing, I'm going to keep looking down to my lower window so I keep letting folks in. But I'm going to, as we continue our kind of deep dive into the plankton today, I wanted to let you know that my slides aren't advancing. Come on, PowerPoint. You and I, we got this. Okay. Enjoy the foxes. And one of the first things that I was going to tell you was actually this, that if you've got some time later on, the Falkor, the Schmidt Ocean Expedition, and the Sebastian ROV are deep underwater off of the coast of Uruguay, and they are diving right now. So if you have an interest in seeing that, there we go. Maybe don't go right now, although both of us, the Falkor is live, we are live, and then they're both going to be recorded and posted later on for your enjoyment at your leisure. Where have we been? Where are we going? This is our week of thinking about things planktonic. So we talked about on Monday these elements. We introduced some terms: meroplankton, holoplankton. We talked about planktotrophic and lectotrophic and effects that phylogenetic consequences, evolutionary pressures to being one or the other. Ecological consequences of adopting either one of those lifestyles. We talked about the Reynolds number and how we live in a big Reynolds world of inertia, and most of the life in the plankton is in a small Reynolds world, and some of it lives there entirely for all of its life, and some of it's only there as its larval stages. But the differences in intuition are kind of striking. So the Reynolds number is going to keep coming up again. And we start talking about some of the challenges associated with living life as a plankton. So we talked about feeding and maintaining position. And then we talked about some of the reasons why we should be very grateful to the plankton in terms of sequestering carbon. Then we talked about one and kind of tipped the cap to one group that we haven't maybe run into before, and that's the Neuston. And that's the group of plankton that lives principally, exclusively, doesn't have a benthic stage at all. It's just floating at the surface. There's not a whole bunch of verticality. There's a slight amount of verticality, but generally they're in the photic zone right at the surface. Where are we going to go today? We're going to continue talking about predator avoidance. And we're going to talk about the largest animal migration in the world. We'll talk about being transparent, because transparency is important, and especially if you're in the plankton. We'll talk about bioluminescence and helmets and spears as elements of defense against the predators, the various and numerous predators of the plankton. And then we'll talk about dimethyl sulfide, DMS, and how that is really important to kind of link some of the earlier elements, some of yesterday's or some of Monday earlier elements in the lecture, and we'll tie it into a nice bow and then talk about emerging planktonic research, and then we'll go away and share or enjoy the rest of the weeks. These are the learning outcomes that I hope that we can identify today, but they're basically appraising, synthesizing, and interpreting how invertebrates in the plankton are avoiding predators, how they can defend themselves against predators, And then some of the consequences, some of the big picture consequences. We talked with carbon sequestration as one of the big picture consequences of the plankton. And we'll talk and make another hook from the plankton into the global climate crisis via DMS. And that's my plan for where we're going. It's a challenging thing being a plankton, maintaining your position and buoyancy, moving at low Reynolds numbers, feeding at low Reynolds numbers. And we've talked a little bit about that. And today we're going to talk about avoiding and defending yourself against the predators, because
it's the hard knock life for us. It's the hard knock life for us.
And I offered that to you as an earworm this morning. It is a hard knock life being a plankton. So one of the ways we talked about avoidance, right? And so the largest animal migration in the world is this daily vertical migration that plankton are conducting around the world in aquatic, in freshwater, and marine saltwater systems around the world. So a periodicity of roughly a day, and it was first described by the French naturalist Georges Cuvier in 1817. So plankton, zooplankton, the ones we're talking about, sink to the depths during the day and rise to the surface at night.
Over 200 years ago, a naturalist in France noticed that small crustaceans were appearing and disappearing on the surface of a pond in a diurnal pattern, meaning they were present at the surface of the water at night, but gone during the day. As it turns out, what he observed was just a tiny part of the world's biggest game of hide and seek. Diel vertical migration is the daily synchronized movement of large numbers of zooplankton and small fish up to the surface of the water at dusk and then back to deeper waters before dawn. This phenomenon has been seen in all sorts of organisms and in water bodies all around the world.
And so the question that I have for you when we talk about this, and I suppose the first thing to note is that I'm not sure how hunky Georges Cuvier was, like he was hunky in this animation. I'm also pretty confident that his notes weren't en anglais, they weren't in English, because he was Georges Cuvier. He was probably writing in French. So what I'd like to do is to have you tell me what some of your hypotheses are about how and why, maybe not the how, but the why. Why might the plankton conduct, why might we see this large-scale diel migration? So in the chat, I've just put the link. You can scan if you're on a phone, or if you've got multi things going, multiple media going, you can scan it. And let me just check over there. Hop over and see. Yep. Oh, nice. Awesome. Okay, as you're filling those in, I'm going to prompt you and remind you that on Monday, Friday, I guess, with the intro spiel, I had asked you to go to the tab of this Google document and find your student number and then go across the 30-odd animal phyla and tell me within which phyla your favorite invertebrate lies. And I think about a third of you have done it, so hooray. And I'm hoping by this Friday, the rest of you will do it. And we'll keep track of that through time. Awesome. This is great. I see lots of you there. Fantastic. Let's draw this up and have a look. So what selective pressures might cause diel vertical migration? Temperature shifts. So maybe they're searching for an optimal temperature. Sensitivity to light, less predation at light. Temperature regulation. So we've got two kind of competing hypotheses. Three, photosensitivity, predation, and temperature, visibility. So again, linking it into the photo world, to light. A circadian rhythm in the predator. So being a response to predators. Predators and food allowance, temperature, oxygen availability, avoiding ultraviolet radiation. Oh, that's interesting. And byproducts of ultraviolet radiation, which tend to be concentrated in the top several layers, at least in aquatic systems. It's kind of a meter in marine systems. less activity at night, temperature, avoiding being seen from below during the day. And that's kind of cool because that links us into some of what we're going to be talking about later on. Awesome. This is great. You've come up with most of the principal hypotheses that we have seen in the literature. So celebrate that. Put your hand up, pat yourself on the head. If you're sitting somewhere communal with friends and you have consent, you can pat them on the back. But let's talk about, this is from the literature. This is kind of the table 1, the list of external variables that may influence the periodicity and amplitude of diel vertical migration. There you go. But it also gives you the out statement at the back. The cited examples do not represent an exhaustive review, but that's fine. We didn't do an exhaustive review either, but I'd like to focus in on the left-hand side. You can use the right-hand side later on via that QR code and the link if you want. If this is a research area that interests you, you can dig into this more. But basically, you've got you've got a great selection of the things that have happened there. So we've got sunlight or responses to light, maybe moonlight or sunlight. Artificial ultraviolet radiation is there. Food availability, temperature. I don't think any of the examples jumped. I'm glancing down now. Yeah, but ice cover, cloud cover, diseases and parasites, those are all fantastic. So well done. And principally what's happening, all of those can work and may have an effect, or a moderating or an accentuating effect. But in most cases, not all, but in most, one of the largest selective pressures, one of the largest drivers of this largest migration in the world is a response of prey, the zooplankton, the small, the little things that are running the world, to predators. And the positioning vertically of the zooplankton in the water column is a trade-off between where they want to feed, which is up high, and what they want to avoid being, which is food for other things like planktivorous fish, which you see here. So the phytoplankton, the primary producers, those algae and plastid containing plankton that live up in the photic zone, that's the principal food for the zooplankton. And close to the surface is where it lives because it needs sunlight. And so that is ideally where the zooplankton would live. So if you had experimental ponds with one species of zooplankton and you put fish in one and kept fish out of the other, probably what you would find is that the zooplankton would stay nice and high at the surface. They wouldn't move up and down so much according to this diel migration. However, if you have fish there and the fish are visual predators, they're going to be cruising around in the photic zone looking to prey on these plankton. And so the plankton will respond to that predatory source and dive. And so up and down and up and down. So yes, ice cover, yes, ultraviolet radiation and some of the byproducts that they might want to avoid here. But those are operating within and around, and temperature plays a role here also because these are ectothermic animals, right? So the optimal growing conditions for them is probably going to be higher where the water temperature is warmer. So all of those come into play, yes. But predation is the principal driving force for this largest animal migration in the world. Let me jump over to the chat. There's Caramel this morning reminding me. And I don't see any explicit questions yet, so we'll scratch Caramel behind the ear, which she likes, and we'll keep going. We're going to talk about, so that's a predator avoiding strategy. Another predator avoiding strategy is to be transparent. So the elimination of optical loss, light bumping into you and returning, and so then people can see you. So if light can propagate straight ahead without any disturbance, things are transparent, like this crustacean. And some level of transparency is found in almost all oceanic zooplankton that are or are not protected by some other means. And so this is a fabulous adaptation that we see in the marine system, that you as all of us kind of operating, we see it to a lesser degree within zooplankton in aquatic systems, but if you are in the marine system for some part of your life history, you're generally going to be, you're going to eliminate optical loss. You're going to try and let light propagate right through you. And there's a whole bunch of ways of doing that, and we'll dive into some of them. To do more justice to this would be a class in itself. But this video that's looping through here, if you can see it, there's a school of squid at the surface there, up in the sunlight. And so the question would be, that we're going to keep pulling at for the next few minutes is, how visible are they to prey above the water surface? How visible are they to prey below the water surface? And there's a number of different ways that will come into that. Some of those are chemical, some of those are biological, and some of those are physical. And so we'll unpack them. But first, I want you to find your annotation tools, because I'm going to use an older plot from the literature. That's not the Dunn phylogeny, but partially because of its positioning. Like, for instance, it has the sponges here as the earliest branching animal lineage, which we don't think anymore. You can put that aside. But we've got 4 different traits here in shape and color. So we've got whether being pelagic is common in a filled-in square. And if your pelagic is rare, it's an open square. And if transparency is common, it's a filled-in circle or an oval. And if it's rare, it's an open oval. So 2 things there that I'd like to ask you about right off the bat. I mean, and you know this, it was kind of in the last bullet if you were reading along, but use your annotation tool. Tell me that you're kind of working along here with me. Is transparency as a trait likely to have evolved one time and then been lost many times, or has evolved independently in multiple lineages? What's your best hypothesis? Nice. Yeah, I tend to agree. And of course, it's not on the slide, but what are we using here to rule out the idea, to kind of prioritize this idea? And that's, of course, Occam's razor, which is that all other things being equal, the simplest explanation is likely to explain something that we haven't. And so life doesn't have to proceed via Occam's razor, but it's a good starting point. And so I would agree with you here. Yes, it has. So again, pat yourself on the head. And so a combination of diel vertical migration and then being transparent, you have 2 different ways of making yourself hard to eat because the predators can't see you. We have some more ways that involve physics. And this is the traits of light as it's proceeding through media, different kind of media. And so transparency, most commonly seen in pelagic things, uncommon in terrestrial or benthic things. And the property that we're going to talk about right now is the use of Snell's window. Throw in the chat if you've heard of Snell's window. Oh, I see you folks in the waiting room. There we are. I'll keep that window up. And I don't see anyone saying that they're familiar with Snell's window. Okay? Hooray. Well, welcome. Let's open the window together. Snell's window, Snell's law, describes the angle that light is refracted at as it enters a medium with a different refractive index. So in this case, air and water. So if we have a fish swimming underwater, or you swimming underwater, whether you're diving, and you're looking up, you tend to see this circle. So this is like a vertical cross-section, but this area with all of these little lines kind of indicating the water coming in, and it's changing the angle is changing as it goes through, changes media from air to water. So that angle changes, and the resulting circle is essentially this. So this window here, where if you are underneath deep in the water, you look up, what you see is an open circle surrounded by darkness. And let's get an explanation here.
Stand white happens here are rolled with some barrels. In the blue regime, the barrel will roll slow, and in the white regime, the barrel will roll faster. Here comes one barrel. When the end sticks out, it will go faster, causing the barrel to rotate. Another barrel arrives with a greater angle with respect to the surface. This causes the outer barrel to rotate for a longer time and send the barrel back into the blue medium again. The regime represents water, where light can move slow, and the white regime represents air, where the light moves much faster. Barrels represented photons.
So as those photons approach this interface between the two media, the angle is changed, the refraction is changed as it enters the medium with the faster turn or the slower turn.
Stand white have.
And so this small differences in the refractive properties of those photons as they're moving through the water are revealed to the animal as a predator and potentially used by the prey. So on a reasonably calm day, this bright in here, this is the circle, the window, Snell's window, and dark, everything out here at the surface is dark, is provided by an angle from roughly 47 to 48 degrees. So we have just over from this angle, if you trace the dark blue lines outside and you've got your protractor out on the screen and you're kind of looking at that, it's just over a 90-degree angle. And so we have just over a 45-degree angle from the vertical. That's what it's talking about, this line right here. And so species of zooplankton take advantage of that. The purple zooplankton here in the window is going to be food very quickly because it's refracting and reflecting light to the fish against a light background. It can be seen. There's no optical loss there. The orange zooplankton is also refracting and reflecting light, but it's highly contrasted against that dark background, and so it is protected. And so we have what are some of the methods that zooplankton have to protect themselves? They can migrate. They can also move laterally in relation to where they perceive their predator. There's a whole bunch of perception that's happening here. And if there's a school of these fish, the angle of any one of these things is going to be different, right? But this is another method, and then you can be transparent. So if you get all of these things together, perhaps you start getting to be a zooplankton that's thinking like positively about yourself, and it's like, I'm going to get out there and reproduce. All right. Now, we talked about transparency. There's also an element that some marine animals have called dynamic transparency. And we see it lots in the mollusks, in the incredible cephalopods. Everybody raise your coffee or your tea or your mug to the cephalopods. Kind of incredible things. And we'll talk about some of that right here. So in the pelagic, so up at the surface near the photic zone, light from the bottom is low and there's little transparency or there's little scatter. So being a transparent thing up at the top, like that school of squid was earlier, that's best. And so if you're a prey item looking from the bottom, the light's passing through. There's no optical loss because you're transparent, like this little ctenophore is here, right? And so you're protected from predators from below. Now, with a bioluminescent searchlight, there are some animals that could bump into you or bump into that, into your body. And so there's a bit of but we don't see a lot of that. Now, at greater depths, pigmentation is better because the protection that you're looking for isn't from light from above, it's from that light, that bioluminescent searchlight of the predator down below, the light that they're making. And so the pigmentation that you would want to adapt if you were a deep swimming ctenophore here would to be pigmented, and so the light isn't going, there's no optical loss and returning signal to that predator with the bioluminescence in the deep, deep water. So protection is inconsequential from the top light because there's not a lot of it. It doesn't get down that. Now, squid, of course, can move in that migration there, or in that vertical transect of the ocean. And so they need to be transparent if they're at the surface. And they need also to be pigmented if they're down at the bottom. So they need to be transparent at the surface on the left-hand side to avoid the fish predator that's seeing the optical loss from below. And they need to be pigmented if they're going to then migrate down and feed, because they're trying to avoid having light bump into them from the predator that has the bioluminescent partner, the symbiosis, that's making its own light down deep. And so this is this kind of amazing property that we see in cephalopods, where they can be transparent when they're up high. They can be pigmented, heavily pigmented against predation as a adaptation against predation when they're down low, and they can switch. And they can switch really, really quickly. And if you remember back to 2700 last year, when we had our limited opportunity together to talk about cephalopods, I played you some videos of the incredible rapidity with which the squid skin can change colors.
The squid Onychoteuthis banksy, and you can see as the blue light hits it, the chromatophores are expanding and it's pigmented, whereas when the light goes away, then it contracts those chromatophores and it's transparent again.
So that chromatophore, when it's being exposed to this blue light, that's the laboratory equivalent of different wavelengths of light from the naturally occurring, from the sun, from the radiation from above. And this is a light signal of a bioluminescent, a bio source of light. And when we see that, or when the squid sees that, the chromatophore opens and it becomes pigmented. And when you take the light away, it returns to that transparent, and it's really quick. So remember, the chromatophores, if you think of, they're little like stretchy granule containing particles where the cell walls can be like elaborated, stretched out, so you're dark, and then contracts so that you're light, transparent, pigmented, transparent, pigmented. And from a biomimetic or a efficient design feature, engineers and humans essentially looking for low energy solutions from the natural world, we're very interested in cephalopod dynamic transparency, because this is, and here's those little what I was calling trampolines here, but this is the squid example that we've talked about here. What folks are interested in doing, and this is of course lots of very frequently military funded research, is to develop clothing that can do the same thing. In addition to the clothing, in terms of it's how transparent you appear in a complicated visual environment, it can also be, and so that's not what's shown here. I'm telling you that with my voice. But what's being shown here is one that can open up and respond to heat, and so can be one that is used to help a single uniform that keeps you cool or at working temperature all the time. Now, I talked about the symbiosis of the predators in terms of being bioluminescent. Now, of course, what we know from our shared experience in the invertebrate world is that symbiosis is everywhere. Everybody say it with me. The mitochondria is the powerhouse of the cell. Right? Okay, that's one kind of symbiosis, a deep evolutionary time symbiosis, but the invertebrate world, if you remember, is full of all sorts of these kinds of things. And here's one with a crustacean species that camouflages itself by making tiny structures in which it can be coated with a thin biofilm that work as an anti-reflective coating, like the anti-reflective coating on many different glasses. And so this is a way that the symbiotic bacteria is actually helping the prey become transparent. So we have some bacteria likely working with the predator to create the bioluminescence, and then we have those that have adopted the other team, and they're going, let's go prey, let's be transparent. That's amazing, right? This is amazing. Caramel doesn't look impressed, but Caramel's hard to impress. Yeah, Gavin, I like it. Just let stuff grow on you. That's my evolutionary strategy, and it seems to have worked in many lineages across time. Now, we talked about the bioluminescence and that kind of blue light that some of the predators, then the diagrams had fish, but of course, what is most of the bioluminescent life in the world? It's not vertebrates.
Whoa! That is just, you are gorgeous, whatever you are. There was this amazing blue glowing thing right there, but now there's just that ugly plankton blob.
Oh, yeah, that. It's the same blob.
Say what?
Well, sometimes plankton glow at night. It's called bioluminescence.
So it's gross during the day but fun and frisky at night, like leather pants?
Yeah, sometimes they glow, sometimes they move around a little bit. They're very sensitive to all sorts of stuff. Light, sound, arguments, personal selection.
And then the clip ends. But yeah, let's raise a hat to the whole team at Bob's Burgers. And my kids will both be delighted when I report to them that Bob's Burgers and this clip that they love also is in this lecture. Actually, my youngest Daniel wanted to acknowledge that plankton are OP, and I don't actually know what that means, but he's telling me that based on his understanding of what we're talking about today, you will agree plankton are OP. Okay. So, bioluminescence.
It's not CGI, it's JGI, jellyfish-generated imagery. In this case, the bioluminescent Atolla jellyfish. It's the kind of amazing display that comes from creatures in the sea that make their own light. And there are a lot of them. A recent study found that among ocean dwellers that you can see with the naked eye, although of course you'd have to be underwater for most of them, 3/4 are bioluminescent. Stephen Haddock did the study.
I always think of it like a superpower. We think of these as like, oh, they're so primitive, these creatures, but they can do something that we could only dream of doing, making light come out of your fingertips or throwing pixie dust of glowing light out at will.
These creatures make light with chemicals in their own bodies. This is how they do it. Luciferase, an enzyme, prompts a chemical reaction in which luciferin molecules absorb energy and then release it as light.
That's amazing. I like Steve Haddock's perspective there. There's a whole bunch. You've actually been introduced to Steve before via some of the links. His research, particularly in the deep marine, is great. And thank you. I now know what OP means. Amazing. And I would have to say, Daniel would want me to know that, or want you to know that he's probably told me that. So one of the reason that these plankton are OP, that marine life, that zooplankton are OP, this production of life, resident, as you heard, perhaps amongst 3/4 of the animals living in the ocean, is actually, from an energetic perspective, is very energetically efficient. So maybe 80% of the energy put into that reaction, luciferin, luciferase combination with oxygen released as light, is 80 to 90% efficient. And old-time light bulbs, like when I was a kid, the incandescent ones, maybe 10% efficient, and the current ones maybe 20%. So again, I'm going to draw in this kind of biomimetic. Why should people who don't automatically care about the invertebrate world really be encouraged to care about the invertebrate world? And one of the reasons, a selfish reason for us, for our species, is that through millions of years of evolutionary history, they have derived low energy solutions to a lot of the same problems that we have cludgingly put high energy solutions in. And now, in this era of the Anthropocene and the climate crisis, we need to adapt a lot and learn a lot of the low energy solutions that they've already come up with.
It's not
light
CGI.
Transparency is maybe one of these things. So this bioluminescence is a form of chemical light, chemiluminescence. There's somebody stomping through. And I don't know if you've put in the chat if you have, but probably you've seen, maybe you've swum in waters that had these plankton that were bioluminescing with this perturbation. And that's kind of amazing. I've done that before as well. So, and we talked it back in 2700, this hypothesis that this actually might be what's the evolutionary selective pressure to the zooplankton in being bioluminescent. So we'll put aside the predators that are using it in the deep water as a way of kind of seeing things that might otherwise be transparent to them. Okay, there's a selective pressure for that for sure. But to the zooplankton in the photic zone, what advantage might there be to this bioluminescence? And what we talked about before is this light bulb hypothesis, this shock hypothesis. And maybe your predator is jittery, because probably predators are jittery because every predator has a predator, and so life is jittery when you're out in the food web. The other hypothesis is that it distracts or blinds. That's the light bulb one. The other is that it marks an area and it says, hey, hey, hey. So it's like a communication across a trophic level. So the zooplankton are the prey. There is a predator. That predator has a predator. And so this flashing might be a signal, a collectively advantage signal from the zooplankton to the predator of their predator to say, hey, come and eat this thing. It's right here. It's right here. It's right here. So it's that's one of the leading hypotheses as to why we would see bioluminescence as an indirect way of attracting predators of your predator to avoid being eaten. And one of the cool things we see with this kind of chemiluminescence, this bioluminescence, is that the emission spectra, like where the light, what the light looks like, it's all over the place. Much of it is blue, and that was the example that you saw in the lab, and that's the example you see with the boots stomping through the ground there, stomping through the shoreline. But you can see across shallow, deep, or benthic life, there's different proportions, and certainly in the deep water, we see a lot of blue, and rarely violet, yellow, orange, and red. And in most cases, and this, if following the light and following the zooplankton is something that you are looking to do for a career, maybe this is because where we see them phylogenetically, it's rare and infrequent. It doesn't seem to be predictive there. And so in most cases, we don't know what the functions and the chemistries are. So there's a lot for us to learn from this end of the emission spectrum from these kinds of taxa. What are some other ways that the zooplankton, that the plankton can defend themselves? Well, now this example that you're looking at 4 species of Daphnia, of water flea. So this is one of the most ubiquitous animals in the ponds of the Arboretum, in the freshwater of Ontario, if this is where you're from. They don't bioluminesce in response to predation. One of the things that they do, and so these are 4 species that are each grown in water that has no predator. This is the same species paired up, grown in water with predators. And you can see that chemically they are perceiving at the base of the antenna. There's an antennule. There's a receptive device they have to read the water, the chemistry of the water, to say there be fish here, or there be dragonflies here, dragonfly larvae, things that will prey upon you. And in response to the water, to the signal in the water, they grow a giant helmet, or more spines, or a giant glowing like alien Earth kind of a helmet. And these spines and these helmets reduce the effectiveness of predator attack. So that's amazing. Okay, so here is Caramel's getting tired. We're approaching the end. And in the last 10 minutes, we're going to talk about the clouds and outer space. But before we do that, I'm going to look down. So yes, some of you have want to. I have swum in water that was bioluminescent, and I was told that, and it was amazing, and I will remember it forever. And I also remember the warning or the look that the people who lived in the area where I did it, when I told them that what I had done, and they were like, well, there's crocodiles in that water as well. And they would be using that as a glowing neon sign of what to eat. So in this case, the zooplankton didn't tell on me, or the message wasn't received. A gourmet or a stinky garlic bald meal. I don't know. Probably junk food. Did I say that most of the bioluminescence in the world is from plankton? I don't know if I said that exact sentence. Most of the life in the 3/4 of life in the ocean is bioluminescent. Based on the individual, plankton probably is, because there's just so many individuals, so many of the small things. So per individual, then yeah, that's probably true. Okay. The next thing we're going to talk about is DMS, or dimethyl sulfide. Dimethyl sulfide is a compound that some people, and I found this, some people, if you've opened a can of corn, that's the smell you're making, or that's the smell that's there. But more likely, if you've been to the shore of an ocean, of a sea, and you've smelt the smell that tells you you're getting close to the ocean, and we often tell ourselves, well, that's the salt. Well, in fact, also what you're smelling is this compound, dimethyl sulfide, which is produced by autotrophic phytoplankton. So this is in this complicated diagram here. We're going to focus on this part, and I'll unpack this, and I'm going to kind of, we'll tend to ignore, just because we don't have time, the part of this chain of this complicated interaction network on the right. But focus here. So we've got algae living in the ocean. And the algae is taking in, it's living in a salty environment, light temperature, nutrients, and it is producing DMSP, which is dimethylsulfionpropionate. And I stumble over that because it's the precursor, and I don't say it as much. I would say DMSP. DMS, dimethyl sulfide, is where the action gets interesting. And that's released when zooplankton graze on the DMSP containing algae. And that DMS, when it's released, is what's making the smell. It's telling you you're close to the ocean. And that signal from the plankton to you, it's kind of indirect to you. It's telling you you're actually near a shoreline. But marine phytoplankton produce this gaseous dimethyl sulfide, which is the most abundant form of sulfur released into the atmosphere and is going to be needs to be part of our understanding of modeling for a climate-informed future. But this is a product of zooplankton grazing on algae. Now, why is that important? It's the smell at the edge of the ocean. It seems like bioluminescence to be this other indirect signal that when lots of zooplankton, but say, imagine the crustacean, the krill, that kind of thing, converting DMSP to dimethyl sulfide, that dimethyl sulfide, the gas that's released, that smell that we're just going, oh, I'm almost to the beach. It's also being read in the air by birds. And the seabirds that forage on the crustaceans that are eating the zooplankton that are eating the algae are then attracted, and they begin to graze. And so the seabirds may benefit the phytoplankton by adding the limiting nutrients via excretion, so like pooping in the water. But this is essentially a chemical communication across trophic levels in the same way that we infer that the bioluminescence might be acting. So more temporary, this is a chemical one. The other signal was physical, the photons, the light. But we've seen examples, so we know these examples exist with seabirds tracking down the dimethyl sulfide. But we also know that when dinoflagellates produce DMS, there is an aviolate. So within the protozoans, within the very small things within the plankton, there is a protozoan, an aviolate parasitoid, that uses DMS to swim towards the dinoflagellate that has just eaten, that's grazing anonymously on the algae, but it's releasing DMS, and the parasitoid aviolate kind of moves its way upstream, swims upstream, and then begins to parasitize it. So there you see several zoospores penetrating into a dinoflagellate host through that flagellate pore for their own gourmet meal. Now, so it's a big part of the food system. It's another way of communicating across trophic levels. And in this case, it's another chemical effect that has a global effect. It's a chemical output that has a global effect, because DMS is an enormous source of cloud condensation nuclei, right? So we've got the DMSP that goes into DMS, and it goes up into the air, and then it bumps into, it is something that water can condense on to form clouds, to then change with a lot of clouds. There's a lot of solar radiation that's reflected, and potentially the temperature underneath those clouds goes down, and it changes then the distribution of water. And so we see, if we're scaling up and taking this class from being one course in one term at Guelph to something that you work on for a career, this is an effect of the plankton on global climate modeling. And it's a crucial element of the sulfur cycle. And this kind of claw hypothesis, which describes this feedback between DMS emissions from the plankton and then creation of clouds and the increased albedo, is really important. Now, and underappreciated and hasn't been in. This is kind of one of the ways that climate modeling, climate forecasting is getting better through time, is because we're trying to introduce these more biotic and so intricate effects into models going forward. So I hope some of you go into that direction. If I'm sorry to cough right in the microphone right at the very end, but it's just because I'm excited to talk about one of the last effects of DMS, or one of the last ways that we've used DMS, and maybe you've actually even heard about it in the news. This, when you were, so you're mostly in third year, this day, September 10th, 11th, in 2023, so when you were in first year, of course you'll remember, there was big news from NASA that was covered by news outlets all over the world, and that was the fact that on a Canadian discovered exoplanet called K2-18b, that they had discovered so 5 or 6 years earlier. So it's a cool dwarf star that's about 120 light years away, that is in the constellation of Leo, if you want to look roughly for it next time you're looking south in a clear sky. That researchers using the Hubble Space Telescope discovered, possibly discovered, and the discovery isn't done yet, the possible detection of dimethyl sulfide on K2-18b. And this is exciting because on Earth, the only place we know that DMS comes from is from life. And so on this little pinprick of light in the sky, that when it's hitting your eyes, that light is 120 years old, there might be the capacity for us to infer the presence of this small chemical that is important to us as we live through the climate crisis, and may be important to us as a signature of life existing on other habitable planets around us. That's kind of amazing. So phytoplankton, zooplankton, plankton all over the world, lots of adaptations to avoiding predators, and perhaps signals that we can read and infer life at a great, great distance. Okay, so I don't see anything new in the chat, and in the last couple of seconds, the only thing that I wanted to do was basically to say, to give, this is a super broad area. This is like invertebrate research writ large that you can do with DNA. You can metabarcode ocean water and read the plankton that are there and discover new species of siphonophores, new species of medusoids, new species of hydroids, new species of zooplankton all over the world. You can make connections to the climate crisis, to other anthropogenic pressures of the Anthropocene associated with water chemistry or temperature. You can research algal blooms. There's just so many different applied ways where an understanding of the invertebrates that make up the zooplankton are so important. So you can use, if you're interested in this, your research can involve satellites looking back down at the Earth or away. It can involve DNA. You can use sonar to bounce off zooplankton to observe these large daily vertical migrations like this, and use it to estimate biomass. You can use sonar. You can use older school like Coulter counters and flow cytometers to count things. And you can remember that all of this is happening on our planet, where we are but one of millions of species, but where we have an enormous impact. And so at the very end of the plankton, at the very last couple moments of the lecture, as Caramel snoozes in the sunshine, I'll just say that the krill that we talked about, that we acknowledged with a tip of the hat in terms of sequestering so much of the carbon that we need to have sequestered from our atmosphere into the sediments at the bottom of the southern oceans around the pole, the southern pole. That's actually a fishery, right? And a lot of it is used in pet food. Maybe not in our part of the world, but in all different parts of the world. And so there's elements to keep on kind of, now that we know, we have an obligation to understand and to give voice for the little things that don't have it. So here's where we've been. Where are we going to go next week? we're going to talk about life history and some big life history things where the plankton are underutilized, or invertebrates are underutilized examples of what we ought to know about life history evolution. There are some things for you to work on. So you're preparing here for your second lab where you're going to go outside. There's a field waiver to sign on CourseLink before you go out. The first of the case studies will be released tomorrow at 9, and you've got till Monday at 9:30 to do that. That happens on CourseLink. And then on Friday, asynchronously, there's no lecture, no shared kind of Zoom time, but the first of the invertebrate R assignments will be released. So there's a couple of videos to watch with that, and then some projects for you to work on. And finally, go away to your next class, but please come back to this Google document and tell me in which phylum lives your favorite invertebrate. And with that, I will say, this has been fun. Have a great remainder of your week, and take care of yourself, take care of those around you. And I'm going to stop sharing in a second.